problem involving two strings, three strings actually. There's string 1, which I will put here, string 2, string 1, string 2, string 3 is on the bottom. Let's see if we can get this to right. 1, 2, 3. Each of these strings, right? This string here, this string is separate. Here's a third distinct string. Each one you can sort of think about as a rubber band. Okay? So when you stretch a rubber band with your fingers, if you stretch a rubber band with your fingers, let's do this over here, and you pull this side and stretch it with your fingers, then right here the rubber band pulls back and it resists the stretch. And that resistance to stretching is called tension. And so what we notice is tension, two things. Tension acts at the end of the rubber band, and at this end of the rubber band. And it points back to the middle of the rubber band, right here. So if we can think of our strings in this way, like rubber bands, we will be off to a great start for these problems. So here's one end of string 1. And here's the other end of string 1. String 1 is stretched, so this end feels some tension up and to the left, pointing back to the middle of string 1. There is tension over here too, by the way, but we don't care about it because that doesn't help us solve this problem. And then, over here, string 2 has one end here and one end here, and each end is where tension acts, and it pulls back to the middle. So tension acts at the end of the string, pointing to the middle. And then we have here string 3. Here's one end, and here's the other end of string 3. So each end has some tension pulling back to the middle. The tension is even and equal in the string, so this value of T3 here is equal to this value. And the final thing, the final force we can draw, is gravity pulling down. And in this case, if we use 10 meters per second squared, then mg is 70 newtons. So we've got the important forces drawn. Let's get started. The system is in equilibrium, which means nothing, in this case, nothing, there's no net forces on any of these points. So right here on the block, the up force of tension is balancing the down force of gravity, hence the up force equals 70 newtons. Right? The block here, the 7 kilogram block, isn't moving. So the up force and the down force balance, they are equal. Right here at this big intersection in the middle, that point is also in equilibrium. So we know then that all of the forces pointing up added together will be equal to all of the forces pointing down. So look at this point and just at this point. What are the forces pointing up? Well, T1 is kind of pointing up, it's up at this angle, and T2 has an, kind of pointing up, it's pointing up at an angle. So each of those has a y component. Because the tension in the left rope equals the tension in the right, because of that fact, we could just say T1 equals T2, or more importantly, the y components of these two tensions, 1 and 2, T1 and T2, their y components are equal. Because the hypotenuse is equal, and they both are at the same 55 degrees, hence their y components are equal. So let's look at our picture and add up all of the y forces acting at this intersection, this big point here that I keep going over. What are the forces acting up at that point? Well, there's T1 pulling up with its y component. And then there's T2 pulling up with its y part. And those two y components are equal, so we combine them as Ty. At this big point here, the only thing pulling down is T3. And we know T3 is 70 newtons. We already found that. Ty then is going to be 35 newtons. and finding the tension T is a simple matter. The equation for y component, the y component of tension is the hypotenuse, so T1 is the hypotenuse, times the sine of 55 degrees. So if we plug in the value of 35, and why is it 55 degrees? Because that's our angle. If we plug in the value of Ty, we divide both sides by sine 35, and we get as our answer. Wait, whoops, hang on a second. This is not 35, sine of 35. This should be sine of 55. So let's replace this 55. And what do we get as our answer when we calculate? About 43 newtons. 43 newtons is the tension in T1 in the rope 1. And because T1 equals T2, 43 is also the tension in rope 2. So what's our trick? In this problem, the trick is the trick is once you've drawn your forces, start by balancing the up and down forces. Start by balancing the up and down forces once you've drawn in all those tensions. Okay, let's do another problem, very similar, but without all the, we're going to make this even simpler. Right? T1, you know what, just call it T, because there's no point in distinguishing T1 from T2, they're both T. And because this is rope 3, I will call this T3, and the block is pulled up by the rope with T3, and gravity, mg, pulls down, in this case with 100 newtons. 10 kilograms times 10 meters per second squared, it's 100 newtons. If the block doesn't move, if it's in equilibrium, so the block is not moving in this case, because it's just hanging there, stationary, then gravity balances T3, hence T3 is the same, 100. If that's the tension at the bottom, right here, at the bottom edge of the string, then that is the same value of tension pulling at the top edge of the string. Both edges are pulled with the same value of tension. That tension is distributed evenly through the rope. That's why the two values are equal. And each of these T's has a y component here. Ty, those are equal. We know that the up forces balance the down forces at this intersection, this point here. So what are the up forces at that point? There are two Ty's pulling up. The down forces are simply the 100 newtons of T3. So Ty is 50. And then we can find the tension, T, in the left and right ropes. The tension, Ty, the y component of tension, equals the hypotenuse T times the sine of 35. So if you replace Ty with 50, we have a simple equation. And how many newtons big is the tension? Let's see. Trusty calculator, Mr. Buttons. 50 over... There it is. You knew I was going to do it. 87 is our answer. Does this make sense? Yes, this makes sense. Right? T, the tension, 87, has to be bigger than its y component because T is the hypotenuse and Ty is just one of the legs. And the legs are not as big as the hypotenuse. So look, ladies, I didn't even draw Tx into my picture. It's not needed to solve, so you don't need to put it in. Last one, let's see how fast I can go. Oh, this is a good one. The tension in the left rope and the right rope is 28 newtons. The tension in the third rope is pulling back toward the center from the edge. So here as well, pulling back from the center. And gravity is pulling the block down in an amount equal to mg. we have to find mass, and we know that T3 equals mg. So to find mass, we will first have to find T3 so that we can plug it into the equation that I've just written. So that's our strategy. That's how we approach this. How do you find mass? You have to find T3 first to plug in here. So find T3. How can we do that? We are going to use the other point just as we've seen in other problems. Balance the up forces and the down forces. Right? Those are balanced. The up forces are the two y components, Ty, and the y components are 28 times sine 45. And that equals the down force, T3. So T3 then is 2 times 28 sine 45. It's 39.6, let's say. Whoa. 39.6. I was looking at the board upside down. 39.6 newtons. So now that we know T3, we come back to this equation. T3, 39.6, is equal to m times 10. Right? We are approximating. And the mass is 3.96 kilograms. And that is easy as pi.